Assalamu alaikum. I'm Farhadul Islam. I'll be talking about OpenRefine's clustering methods. First, let's discuss about clustering first. What is clustering in OpenRefine? The cluster function groups together similar but inconsistent values in a given column and lets you merge these inconsistent values into a single value you choose. This is very effective where you have data with minor variations in data values. An example, names of people, organizations, places, classification terms, etc. Now, what are the clustering types in OpenRefine? OpenRefine currently offers two broad categories of clustering methods, such as key collision methods and nearest neighbor methods. Let's talk about the key collision methods in brief. Fingerprint method, N-gram fingerprint method, Metaphone 3, Cologne Phonetic, Daish-Makotov, Wade and Morse are the key collision methods, and the last four methods are basically phonetic clustering methods. To give the examples of nearest neighbor methods, which are Levenshtein distance and ppm. Let's talk about the comparison between these two methods. First, let's come to the key collision methods. It's comparatively fast, and key collision methods are based on the idea of creating an alternative representation of a value or a key that contains only the most valuable or meaningful part of the string, and buckets or bin, as it's described inside OpenRefine's code, together different strings based on the fact that their key is the same. On the other hand, nearest neighbor is comparatively slow. The nearest neighbor methods, also known as k and n, provide a parameter, the radius or k, which represents a distance threshold. Any pair of strings that is closer than a certain value will be binned together. Let's start with fingerprinting method. The fingerprinting method is the least likely to produce false positives, which is why this is the default method in OpenRefine. The process that generates the key from a string value is the following: removing the leading and trailing white space, changing all the characters to their lowercase representation, removing all punctuation and control characters, normalizing the extended Western characters to their ASCII representation, split the string into white space separated tokens, sort the tokens and remove duplicates, join the tokens back together. There are several factors that play a role in this fingerprint. Because white space is normalized, characters are lowercased, and pronunciation and punctuation is removed. Those parts don't play a differentiation role in this fingerprint because these attributes of the string are the least significant in terms of meaning differentiation. These turn out to be the most varying parts of the strings, and removing them has a substantial benefit in emerging clusters. Because the string parts are sorted, the given order of tokens doesn't matter. Normalizing extended Western characters plays the role of reproducing data entry mistakes performed when entering extended characters with an ASCII-only keyboard. Note that this procedure can also lead to false positives. Now comes n-gram fingerprinting. The n-gram fingerprinting method does the following. It changes all characters to their lowercase representation. It removes all the punctuation, white space, and control characters. It obtains all the string n-grams, sort the n-grams, and remove duplicates. Join the sorted n-grams back together. Normalize extended Western characters to their ASCII representation. So, for example, the 2-gram fingerprint of Paris is Aries Perry, and the 1-gram fingerprint is APERS or AIPRS. Now, why this method is useful? In practice, using big values for n-grams does not yield any advantage over the previous fingerprint method, but using 2 grams and 1 grams while yielding many false positives can find clusters that the previous method didn't find, even with strings that have small differences. with a very small performance price. Now comes the phonetic clustering part. They identify letters that sound the same when pronounced out loud and assesses text values based on that, such as knowing that a word with an S might be a mistype of a word with a Z. They are great for spotting mistakes made by not knowing the spelling of a word or name after hearing it spoken loud. Metaphone 3, Phonetic, Daich Makotov, Beta Morse are the examples of phonetic clustering. Now let's give some examples of these methods. Metaphone 3, fingerprinting, is an English language phonetic algorithm. For example, Ruben Jevokiant and Ruben Jevokiants share the same phonetic fingerprint in English. Colon fingerprinting is another phonetic algorithm but for German pronunciation. Daich Makotov is a phonetic algorithm for Slavic and Yiddish words, especially names. Beta Morse is a version of Daich Makotov that is slightly more strict. Now comes the nearest neighbor clustering methods. First comes the Levenshtein distance, or known as edit distance. The Levenshtein distance between two words is the minimum number of single character edits required to change one word to another. Each character that gets changed counts as one distance. New York and New York without space have an edit distance value of 3. How? We need 3 edits here. First of all, capital N to smaller n, capital Y to smaller y, and of course remove space. It can do relatively advanced edits, such as understand the distance between m.Makiba and Miriam Makiba, which has an edit distance of 5. But it may create false positive if these distances are greater than the other. Simpler transformations, such as the one character distance to b.Makiba, it makes the name another person entirely. Now comes PPM, prediction by partial matching. Prediction by partial matching is an adaptive statistical data compression technique based on context modeling and prediction. We predict the next symbol of the sequence by having some context remembered. We determine the order of ppm by k. If k is context and k first symbols has not been seen yet, we use smaller context. If the symbol we encode was seen before, we use its counter. If the symbol wasn't found to encode escape, dividing by escape's counter by number of all symbols occurred in this context and escape's context, then we drop it to a lower context k minus 1. If we are in context 0, we encode the symbol with the probability pi. And if the symbol was not seen before, which means we are in minus 1 context, we encode it with 1 by source alphabet. Now we will see how to use clustering methods on OpenRefine. Before showing you how to work with clustering, I have to mention something again, which is why we use clustering on OpenRefine. This is basically used for detecting pretty similar words, which can be typos or maybe duplicates or maybe with white space. So we use clustering to find those issues. Now we'll start with a very simple example here. Let's choose publisher and facet it. And if we choose this, we'll see the frequency distribution here. Let's go back and click this button. Now we get our results, but if we see here, we chose the key collision method and the keying function. In this case, we chose fingerprint method, and if we choose n-gram fingerprint, we get the same results, and the same goes for other methods as well. And if we choose nearest neighbor, we get the same one, and ppm. So ppm didn't detect any issues there. So here's an example how different algorithms detect different kind of issues. So in this case, ppm is not a good algorithm. So let's go back to our fingerprint method. Now, how to fix this issue? Basically, they mean the same thing, but there's one extra space. So if you select all and merge selected and recluster, this issue gets fixed. So let's close it. And previously there were 7 choices. Now you'll see 6 choices. 6 choices will turn 96. So you can see how this thing gets done here. Let's choose another one. It can be authors. Facet text facet. So there are 883 choices. You can see the frequency distribution. Now if we cluster it, so firstly in fingerprint method you won't see any clusters, which means in this method we won't find any issues. If we choose n-gram fingerprint, we'll find these issues. So there are issues, but these might not be the same thing. So it depends on the data cleaner or the data scientist that if you want to clean it or not. They can be the same person, and they can also be a different person. So it depends on the data analyst or data scientist. Now if we choose a different method again, now Metaphone and the rest of the algorithms basically finds the phonetic issues here. So there are some similar names which are pronounced almost the same. So in that sense, these algorithms, these last 4 algorithms, find these kind of issues which are pronounced in similar way. Now if we choose nearest neighbor and Levenshtein distance, you saw it took some time as this algorithm is not that optimized like fingerprint method, but it found some issues. And as you can see, it's pretty much the same. There's some space issues, and if we want to correct this one, just select this and merge select, and you'll see it got fixed. Now if you don't want to fix this one, just leave it as it is. And if we choose ppm, it took a lot of time, and it found many issues with the data. So again, it's up to you or the data scientist who is going to fix the data. Now it actually depends on the algorithm. As I've mentioned in the slide presentation, not all algorithms are the same. It finds different kind of problems, and you have to know your data very well for that, and you have to know what's your goal. So if you want to keep everything the same, or if you want to keep everything simple, you can just select merge all. But if you want to keep everything very correct, in that sense you have to be more specific with your data. So that's all from OpenRefine's clustering for now. Thank you.